Hi everyone, welcome to Math 111. This is Scott, and let's get started. We're going to start with section 3.1 from the OpenStax free OER textbook that I mentioned in the email, and you can also see on the syllabus. So 3.1 is our first introduction to functions. And in particular, what we're going to do in this section is define functions, function notation, and do some basic things with some functions. So first off, what is a function? So a function is any procedure so examples might be formula, graph, table, etc. Mostly those three. Is any procedure that can be used to generate output values when given input values. So you give it input, it gives you output. Now there's one catch here. Specifically, each input can only generate a single output value. So if you think of a function as being a way of answering a question, you feed it a number, it gives you an answer. You feed it that same number again, it had better give you that same answer again. No multiple outputs correspond with the same input. From the same input value. Okay, now the notation that we'll use for functions is as follows. This is what's called function notation. So the way we will write this is if x is going to represent the input variable and y is going to represent the output variable, this is the input or independent variable, y is going to represent the output or dependent variable, and we say independent because x can be anything, you get to choose it, and we say dependent because y's value depends on what you've chosen for x. So if x is the input or the independent variable and y is the output or the dependent variable, then the way we write this is f parentheses x equals y, and the way we read this is we say f of x equals y. And what that means is that the function's name here is f, and whatever the input is going to be is what goes inside these parentheses. And then the answer, the output, is whatever comes on the outside, on the other side of the equals. So for example, So for example, if I were to say f of 3 equals 4, then that would be specifically identifying 3 as the input and 4 as the output. So this is the way to read the notation. Now, when it comes to functions, no matter what method the function is given by, whether it's a formula, a graph, a table, or something else, there are two sides to the function value coin. One is plugging in a value, and we call that evaluating. Evaluating means plug in an input value and produce the output value, versus the other side, which is called solving, where we set the whole function equal to a specific output value and find the corresponding input value. Set the output to a certain value and find its corresponding input. Alright, now the first task that we are going to encounter in your homework, for example, is an equation will be given that involves x's and y's, and it'll be up to you to determine if it satisfies the requirements for being a function. So equations as functions. The idea here is that if we are given an equation that involves x and y, so given an equation involving x and y, we can determine whether y is a function of x, and by that what we mean is y would be the output, x would be the input. We can determine whether y is a function of x if, or I should say by, step 1, solving for y. And step 2, once we have solved for y, if we can, should say if possible, maybe we can, maybe we can't. So once we have solved for y, if it's possible to do so, then we need to look at whether the formula that we get is well defined. In other words, does it only give one value for each value of x? So solving for y, and then determining whether the result gives only one y value for each x value. All right, so hard to say. Is this easy? Is this hard? Who can tell? What it needs is an example, or a couple of examples. So first off, let's try an example of an equation like this. So first example A. So question here is y a function of x. First example, let's take an equation such as y plus x squared equals 1. Now notice that currently, as written, y is not solved for. X and y are just floating around together on the equation, they're even on the same side. The y has not been isolated yet. Step 1 is to isolate the y. So to do that, we look at this equation, and to get the y by itself, it's going to be no more than just subtracting an x squared from both sides. So what that's going to look like is y is going to equal 1 minus x squared. All right, step 1 accomplished. We have found that y can be isolated pretty easily. And now the question is, will each value that we plug in for x produce only a single value for y? So, looking at this, there's no reason to think it wouldn't. Whatever value you pick for x, we just square that, 1 minus that, and that'll give us the value. The thing that we would be looking out for is if there's a plus minus type thing or something like that getting in the way. But sure enough, each value of x, whether x be 0, -1, 3, pi, a million, no matter what value you pick for x, it's only going to give you one value for y, and so the answer is yes. Yes, it is. Now let's put the square on the other foot. What if it's y squared plus x equals 1? It's a very similar equation, but an important difference. So step 1 here is to try to solve for y as it was before. Now, first thing we would do is subtract the x from both sides, very similar to what we did last time around. What we'd have is y squared equals 1 minus x. Now, the y is not yet isolated. To isolate the y means to get rid of everything around it, whether it be a coefficient or, in this case, a power. So we will undo the square by taking the square root. However, when that happens, these do not actually cleanly cancel out the way you might be thinking. We have to be very careful about this, because if y gets squared and then we take the square root, then if y had started out as a positive number, it would stay positive. But if y had started out as a negative number, squaring it would turn it positive, taking the square root would keep it positive, and so no matter what, the y value here, once we ran it through this ringer, would end up producing a positive over here. So to account for the possibility that it could have been the negative version to start with, we have the classic plus-minus situation, which occurs whenever you try to solve an equation by taking a square root of a square. Now, when you get this situation, when you have a plus-minus, that is a classic telltale sign that the y is not well defined by this formula. If I pick a particular value for x, for example, I pick a value of let's say 1/10, then 1 minus 1/10 is going to give me 9/10. I take the square root of that, whatever it is. There's going to be the positive version and there's going to be the negative version, two values of y for the same value of x. So the answer here is no. Two y's for each x. So that's what it looks like when it all fails. And that's actually the main thing to look for. The make or break step here is recognizing the plus minus. The plus minus is the dead giveaway. That means it is not a function because it's not well defined. There are going to be two outputs for each input. All right, now, supposing what we had was just a formula, let's see how we can do the two sides of the function coin. So, formulas. And let's have as an example something like this. So the way we write this is we say f of x equals, and then what we put is the formula involving the x. So we could have something like 1 plus 2x squared. Something like that. Now, if we want to evaluate this, then what we would have to do is take whatever the input that we are being given and put that in everywhere there used to be an x. So, evaluating. What this means is replace x by a new expression. It might just be a number, or it might be more complicated. So replace x by a new expression. As an example here, let's say, keeping that same f, the same f up there, let's say we wanted to do f of 0, f of 3, f of negative 2, f of a, sorry, let's say negative f of a, say f of negative a, and then finally let's say f of a plus h. So the first few of these just involve putting in specific numbers for the x. The next ones involve doing something a little different, which is to modify the formula in some way. So this one is saying, put an a in for x and make the whole formula the opposite of what it used to be. Put a negative in front of the whole thing. This one is saying, where there used to be an x, put a negative a. And this one is saying, everywhere there used to be an x, now shall be an a plus h. So as an example, or as this example goes, let's start with this. So f of anything is equal to 1 plus 2 times that thing squared. That's what that formula is basically saying. Everywhere there's an x, put in whatever your desired input is going to be. So in the very first case, what we're going to have is 0 and 0 for all the x's. Now, the way that's going to shake out is we will evaluate this, and we'll evaluate it according to the usual mathematical order of operations. So we would start by working our way from the square out to the multiplication over to the addition. So it's going to be 0 squared, which is 0, times 2, still 0, 1 plus that, which is going to be 1 plus 0, or in other words, just 1. So that's f of 0. Just everywhere there used to be an x, used to be called f of x, now it's f of 0. Everywhere there was an x, put in a 0. And now, let's put in a 3 for every x. So that's what f of 3 means. So once again, what we are doing here is we are just thinking of the input as going in that spot and that spot. The input was originally an x, but now it's going to be a 3. In goes a 3, in goes a 3. So we've got f of 3 equals 1 plus 2 times 3 squared. So now we evaluate it again, working our way from the inside out. So first we square the 3. Then we multiply it by 2. Alright, so let's figure that out. So 3 squared is 9, times 2 makes it 18. Then we have 1 plus 18. So 19. So that's what we get when we evaluate f of 3. Now, nothing is different morally in putting in a negative 2 for the x. But we have to be very, very cautious about negatives, and in particular, we have to make sure that we are very respectful of parentheses everywhere they belong. So here, wherever there was an x, we're now going to do a find and replace and put in a negative 2. So negative 2 is what's getting squared here. But negative 2 all squared is going to be making positive 4 because it's negative 2 times itself. Negative, negative, positive. So it's going to make positive 4 times 2 is going to be positive 8 plus 1. Oops. 1 plus positive 8 for a total of 9. And let's see, where are we now? Negative f of a, I should say. So negative f of a. What this means is take the entire formula for the function and put a negative in front of that and put an a where there used to be an x. So it would look like this. Negative, and you'd use parentheses because there's more than one term, so the negative needs to be even-handedly applied to both. And so then we would distribute the negative to make negative 1 minus 2a squared. And there's that. Now let's go down one more and the next one is f of negative a. So no matter what the input is, f of whatever it is going to be 1 plus 2 times whatever that is squared. So whether that be a number or something else, this is where it goes. In particular here, what goes in there is a negative a. Now this, not being a number, but being instead an algebraic expression, just means we're producing a new formula that's inspired by the old one, but slightly different. So what we'll have here is 1 plus. Now, looking at this, when we have a negative a and we square it, then the negative a times negative a is going to cancel out the two negatives, and what we'll end up with is 2 times just straight up a squared. Not negative a squared, but just a squared. So that's what happens there. The negative a gets all eaten up by the square. Squares do not respect negatives. If this had been a third power, that would be different. But squares do not care about negatives. Now, the most complicated of the variations on this is when we take a more complex algebraic expression and we put that in place of x. So everywhere there used to be an x now is going to be an a plus h. And what that means is that what we are going to be dealing with here is 2 times a plus h repeated. So we're going to have to carefully mind our parentheses here, and then this is a situation where we have to do what is called foiling, where you have to take every term of each of these two factors and distribute it to the other factor. So we're going to have still 1 plus 2 times, and then here we're going to have first with first, which is going to be an a times an a or an a squared. We're going to have first with second, and that's going to be an a times an h for AH. Then we're going to have a second times a first, and that's going to produce an H times an A, which is again just going to be AH if I write the factors in alphabetical order, which is the usual way. And then finally here we're going to have an H times an H, which is going to make an H squared for the final factor. Now I put parentheses around this entire result because there was a 2 that was being multiplied by this entire factor. So this is going to have to be distributed to all the pieces. And that's going to give us a 1 plus 2a squared. And here we have AH plus another AH. So it's going to be, when we distribute it, 2AH plus another 2AH for a grand total of 4AH. And then finally plus 2h squared. And if there were any like terms, I would now combine them. But to be like terms means you have to have the exact same variables to the exact same powers. And no two terms of this, so the terms being that one, that one, that one, and that one, have those same terms, the same factors to the same powers. We have just a constant, we have an a squared, we have an AH, we have an h squared. No two match up. So this is what it means to evaluate the function at various inputs, starting with just straight up numbers, working our way more abstractly into algebraic expressions. But then there's another side of the same function coin, which is not to plug in a specific number, but to solve. So this would be another example using the same function. So solve f of x is equal to, and then let's say 51. So what does this mean? Well, instead of what we had before, where we were given an input and plugging it in, what we are now given is an unknown input and 51 for the output. So what this means is that 51 is equal to 1 plus 2x squared. And to solve something like this, what we're going to have to do is we're going to have to peel away layer after layer around the x in order to get at what is inside. So if this had been a more complicated expression, we might have to, for example, move everything to one side, attempt to factor it, or use the quadratic formula. But as is, it's the kind of thing that only has one x, so we can just work our way from the outside in, peeling away layer after layer until we're just down to the x. So first we get rid of that 1 by subtracting 1 from both sides, which will give us 50 equals 2x squared. Now, continuing working our way from the outside in, we now have to get rid of that 2, which we do by dividing both sides by 2. So the 50 is going to become a 25, and we're going to have over here just an x squared. And now what we have is the square of x equals 25, and to undo that, we need to take the square root of both sides. But when we do this, we're in the same position as we were a little while ago when we were solving for y. And what we have here is not just 5, the square root of 25 is 5, but that's not the only solution to this, because when we square x and then take the square root, we're missing the possibility then that x could have been negative to start with. So we have x is equal to plus or minus 5. So those are our two solutions. Now, there can be two solutions to one of these equations because we're not talking here about the same x value producing two y values. We're talking about two different x values sharing a y value. Nothing in the rule of functions prevents that from happening. So this is still within the realm of functions. Now, things could get more complicated if we have a more sophisticated equation to solve. This one, we got lucky because there was only one copy of the variable we were solving for. But we might have a different situation. So let's say we have something like if L of t. So the letters for functions can be anything. Typical letters are F, G, and H, but they can be anything. They can be L's, they can be M's, they can be anything you like. And the typical letters for the input will be frequently X, and then very often also T, and then other letters besides that will be a little bit less common. But here we're going to have another function. We're going to call it L of t, and it's going to equal 2t squared plus t. So t is the input here, and then the output is going to be the result of this. Then, if that's our function, then solve L of t equals 1. So what we've got here is a specific number given to us, not for the input, but for the overall output, for the result. So what that means is that 2t squared plus t, that's what it means to be, that's what L of t means, is equal to 1. And this is what we are trying to solve. Now here we have multiple copies of the t floating around, so if we're going to try to solve this, what we have to do is something quadratic. In particular, we're going to have to move everything to one side, have a 0 on the other, factor if we can, and if we can't, then we will have to use the quadratic formula. So we move everything to one side, we subtract the 1 from both sides, and we get 2t squared plus t minus 1 equals 0. And now the task would be to try to factor this if we can. Now, turns out we can factor this, and there are different methods you might enjoy for attempting this. There's what's called the AC method, which is also called factoring by grouping, or there is what's frequently referred to as just unfoiling, where you just come up with the combinations that can make the thing that you need to be the result. So here you can look at the first factors. The first two factors here are going to have to multiply together to make a 2t squared. So one way of doing that is just a 2t and a t. Yeah, that's pretty much the only way. Now the other two factors here are going to have to multiply together to make the final term, which is going to be negative 1, which means we're going to have a positive 1, we're going to have a negative 1. Now thinking about how this is going to play out, we're going to need, so those multiply together to make that. One of these is going to be a plus, one of these is going to be a minus. We have to figure out which is which. Now what we need to happen is when we multiply this times this, this times this, this times this, and this times this, and add them all up, we should get the original thing. So the important thing here is we need this times this, and this times this to come out equaling t. Well, we have 2t, and then our choice, so it could be either 2t or negative 2t, and then it's either plus or minus t. Now, if we're trying to shoot for t here, then we can see that the 2t is going to have to be times the positive 1, and the 1t is going to have to be times the minus 1. So that gives us our two factors, and you can again factor this by all kinds of different methods, and whatever method you're most familiar with, go ahead and use that. But once we have it factored, then what we can do is we can apply what's called the zero product property, or zero product principle, and we can break this one equation up into two equations. if 2t minus 1 times t plus 1 equals 0, then that means either 2t minus 1 was equal to 0, or t plus 1 is equal to 0. Now, each of these, then we can solve by just peeling away layer after layer. So add the 1, and we get 2t equals 1. Divide by 2, and we get t equals 1/2. Over here, subtract the 1, we get t equals -1. And what we've got is the two possible solutions here, that t equals 1/2 or -1. All right. Now, solving is the other side of the function coin, the other side being evaluating. There's a specific kind of evaluating that you'll see a lot more in calculus than here, but we're just going to mention it once and then more or less move on with our lives, but that is what's called the difference quotient. So this is a specific arrangement of a function, and it looks like this. So the difference quotient is going to be equal to f of x plus h minus f of x divided by h. In the next section, we'll get a better idea of what this is actually supposed to mean. Actually, I apologize. Section 3.3 we'll get a better idea of what this is supposed to mean, but for now, we'll just take it for what it is. We'll just try to figure out, based on what the symbols are or what's floating around here, what this must mean. And as an example, let's find the difference quotient of f of x, which is going to equal 3x squared minus 1. So what this question is asking us to do is take this particular function, and we are going to use that as the f in this whole arrangement. So we're going to take f of x plus h. We're going to subtract f of x. We're going to divide the whole thing by h, and we're going to simplify the result as much as we can. So, here we go. And I should say the subtext here is simplify. So the goal is to simplify the result as much as we can. So let's think about how this is going to play out. So the difference quotient is equal to something minus something all over h. Now the first thing here is going to be f of x plus h. Well, as we evaluated before, what we just do is put the desired input everywhere there used to be an x. So where there used to be an x here, there's going to be an x plus h. And over here, what we're going to have is simply the original function classic f of x. Now, if we want to simplify this, what we're going to have to do is tread very carefully and make sure we evaluate piece by piece, expanding where we need to expand, combining like terms where that's appropriate, and then canceling whatever we can cancel. So here, working our way from the inside out, the typical way of evaluating a mathematical expression, we're going to have 3 times, it's going to be x plus h, all minus 1, and that's going to be the end of that. And then here, what we're going to have is minus still 3x squared minus 1 all over h. Now here we're going to have to do the classic foiling dance where we multiply first with first, first with second, second with first, second with second. So we're going to have 3 times. Now it's going to be x times x, which is x squared. Then first with second, so it's going to be x times h, which is going to be hx. Then second with first, which is going to be h times x. And then second with second, which is going to be h times h for h squared. So then we end that parenthesis, which indicates where the 3 is getting multiplied, and we do subtract 1. Here, I might as well go ahead and distribute that negative right there to both of those terms. So we've got minus 3x squared, and then minus negative 1, so plus 1, all divided by h. Now here, let's distribute the 3 and combine these two like terms. So hx and hx will combine. So it's going to be, what we're going to have here is 3x squared. We're going to have 3hx plus 3 more hx for a total of 6hx plus 3h squared minus 1 minus 3x squared plus 1, all divided by the h. Alright, now we continue working our way as gently as we can from the inside out, just doing very small little baby steps, combining like terms, canceling things, doing stuff like that, until we can eventually, hopefully, end up with something simpler. So now we take a look at the top, the entire top, and we look for any like terms that can be combined. And right here, the 3x squared and the negative 3x squared are not only like terms, they cancel each other. And the same thing is true about the negative 1 and the positive 1. So then we look at what we have left. We have 6hx, we have 3h squared on the top. And we have that all being divided by h. Now, you might be tempted to do something like just cancel that with that, but be careful about that because we can only cancel a factor from the top with a factor from the bottom if it's a factor of the entire top and a factor of the entire bottom. So before we can go canceling the h with the h, we have to pull the h out of the top so that it is a factor shared by the whole top. Oops, not squared, 6x. So we pull the h out from the first term, and we're going to have just 6x. We pull one of the two h's out from the second term. It's going to give us 3h. And then what we have here is a factor of h on the top, a factor of h on the bottom, so those can cancel. And that just leaves us with 6x plus 3h. And that's the most simplified that can be. Now again, this is kind of a one-off task for us, but in calculus, so Math 251, when you get into that, this is going to be actually the linchpin of that, the central operation that all of calculus revolves around. But anyway, that's that for us, and now we're going to move past formulas for a bit and think about graphs. So first off, if I just draw a graph on a piece of paper, then that may or that may not represent a function. And to determine it, what we have to do is first off agree on the layout as far as input and output. Now, The classic standard way to arrange these is that what is typically called the x-axis, or the horizontal axis, is going to be the axis where the input values are. And then the vertical axis is going to be the axis where the output values are. And then if you have some graph and it represents a function, let's say f of x, then every point that is on the graph has its coordinate from the x direction and its coordinate from the y direction. And together, those two coordinates give you a connection of input value to output value. So for example, let's say that we had some point on the graph and it was an x value of 3 and a y value of 2, just for example. Then from the graph that we've got laid out here, this is going to be an x value of 3 and a y value of 2, and it's the usual ordered pair. So this represents the fact that f of something equals something, and here it's the x that goes there and the y that goes there. So it's going to be f of 3 equals 2. So the points on the graph correspond with a function value. So input this produces output that. Now, not every formula makes a function. It has to be well defined, and the same is true for graphs. And the way that you test whether a graph is a well-defined function or not is what's called the vertical line test. Or commonly abbreviated VLT. So the vertical line test, the VLT, it gives you a way to determine whether a given graph is indeed a function or not. And the important thing about it is that if you have a graph, no two y values can have the same x coordinate. So for a graph, to represent a function, no two y values can correspond with any x value. So in other words, thus, no 2 points on the graph can be on the same vertical line. So as an example, function or not? So for example, let's take a graph like this. So let's say we had a graph that was going zigzaggy around like so. Well, if you look at the y-axis, for example, we can see here a vertical line that crosses the graph 3 times. What that means is the same x value, the x value of 0, corresponds with that y value, and then that y value down there, which would mean that the function is not well defined, so actually it's not a function at all. So no. The reason is it fails the vertical line test. All right, well, what about a function, or sorry, what about a graph, I should say, like this? That's a pretty classic looking graph. Goes up, goes down. And the answer is yes, this would be a function. It does not fail the vertical line test. It passes it. And then finally, one thing that you might be that might be misleading about this is some things that you might think would be bad are actually okay. Namely, we could have gaps in the function. So we might have the function go loot and then loot, something like that. There could be a big gap in it, and that's fine. No problem. And actually, it can be even crazier. We could even have a little bit of a little piece right here, which at first you might think is going to be bad news. But then remember, what does it mean in a math class when a graph is drawn with a circle that's filled in versus a circle that's not filled in? The not filled in circle means that that point is not actually included. It's like I took a little tiny pair of tweezers and plucked that one point right out of that graph, which means that that there are not 2 points that are actually along the same vertical line here, and so we just barely, by the skin of our teeth, pass. Okay, so that's the vertical line test. Now, the two sides of the same the same function coin are still in effect for graphs. So evaluating and solving. So let's take the function. So as an example, we'll just draw ourselves a nice big swoopy function that goes like that. And let's say that some of the key values here would be something like 3 for the y value there. Let's say this is equal to 4 for the x value. Let's say this is equal to -4 for the x value of that. Let's say this one is equal to 10. And then let's say furthermore that this right here is going to be 8 for the x value. And let's say it's -2 for the y value, and then let's say the other point over here that's at the same y value is at -6 for x. Okay, now the kinds of things we can be asked to do would be, for example, evaluate f of, let's say, 8. So what this means is that the x value here is 8, and it's up to us to find the y value. So x coordinate of 8 puts us here, and the point on the graph at that x value is that one down there, which has a y value of -2. And then conversely, we could have to solve. And we could solve, say, something like f of a mystery x, it's for us to find that, is equal to, let's say, -2. Then it's up to us to find all the values of x that would make this happen. The y value is given to us, the x value is what we want, and so we know already an x value that would do this is 8. But there's another one, and it comes to us from the left side of the graph. Sorry, that was off screen. All right, so I just was writing down what I was saying. And then the other one on the left is going to be -6. Okay. Now the The last topic from a graph is the topic of one-to-one functions. Now, every function is guaranteed to only produce a single y value for each of its x values. But sometimes it goes the other way too, and that's what it means to be a one-to-one function. Each one x value gives one y value. So the way to test this is basically whether it passes not the vertical line test, but the horizontal line test. So functions that pass the horizontal line test are 1, 2, 1. And we'll explore later what that actually means in more detail, but for now, all we need to know is the horizontal line test, which is basically the tipped over version of the vertical line test, is how we're going to determine that. So as an example is the following. One to one. All right, and as an example here, example A, is this going to be 1 to 1? So we're going to have a graph that goes like so. So it swoops down, swoops up. Now the horizontal line test is just like the vertical line test, except that it pertains to horizontal lines. So here what we have are 3 different points that all share the same y value, but have different x values. So that's a failure of the horizontal line test. Which means the function is not 1 to 1. Conversely, if we had a function such as this one, where it never quite doubles back on itself vertically, or horizontally, I guess, if we have a function like this, then it would be, yes. It passes the horizontal line test. All right, and now tables. So tables are very easy to use as long as the function that you're talking about has its values that you're wondering about on the table. So the important thing about a table is that it gives you the x value and corresponding output value. So it gives you the input value and the corresponding output value. And you might have something like 3, 5, 7, then outputs of -2, 1, -2. This could be just as an example. And then you could have to evaluate this. Evaluate f of 3. So what that would mean is the x value here is 3. And the question would be what output goes with that. So it would be -2. Conversely, we might have to solve. F of x equals 1. So here, this is the y value that's being given, and it's the x value that's being wanted. And so the 1 is fixed, so it's a 5 that we are supposed to fit into the x spot. So that means x has to equal 5. Whenever the question says solve this or solve that, the answer should always be something like x equals this, x equals that. Or sometimes you might give it in some sort of a set. But typically when solving equations, you just need to find the missing value of the variable, say x equals this, x equals that, t equals this, t equals that, etc. All right, and now for the last task, a little gallery of what are called the toolkit functions. So this is what the book calls them. They're sometimes called the gallery of basic functions, the library of functions, things like that. So these are a couple, or not a couple, there are several basic functions, and we just want to take a look at what the silhouettes of these graphs will look like. It'll make it more convenient for us later on to just have a sense of what, generally speaking, these particular functions graphs look like. So first off, there is what's called the constant function, which has as its formula f of x just equals c, some constant value. So that is the same as the equation y equals c, which is the equation for a horizontal line at a y value of c. So a constant function is just a horizontal line. Then we also have what is called the identity function. And the identity function has a formula f of x just equals x. Now what this particular function's graph looks like is the set of all the points where the y value is the same as the x value. So in other words, it's going to be going right up diagonally with slope of 1. So this is the same as just a line y equals x. So slope of 1 going right through the origin. The next from our toolkit is what's called the absolute value function. And the way that looks is f of x equals the absolute value. So that's looks like parentheses, but just straight bars. And then the graph of this, when x is positive, the absolute value just gives you the same old value again. So it's nothing special there. But when x is negative, it gives you the positive version of that. So then what you get is the version that is always above the x-axis. So the y values are never negative here. And it produces the characteristic v-shaped function. V for value. Then there is what is called quadratic function or square function. And that one is again classic. You've all seen it. You all love it. It's just the smiley little parabola shape, as it's called. A shape known even to the ancient Greeks, turns out. Now, the next level up from a quadratic is what's called the cubic function. And so the formula there is f of x is equal to x cubed. And the most important difference, if you are raising something to the third power instead of raising it to the second power, is that unlike with a quadratic, when you're squaring things, here, if a negative goes in, a negative will come out. So it looks a lot like the parabola, except that when you put in a negative value, you get a negative answer. So it's got one side up, one side down. That's the big difference between even versus odd for exponents, is that even powers always produce positive answers. Odd powers produce positive on one side, negative on the other. Then the next on the toolkit is what is called the reciprocal function. And what this looks like is f of x equals 1 over x. So it's called a reciprocal because the reciprocal of a number is what you get if you do 1 divided by it. So the reciprocal of 2 is 1/2, for example. And what this looks like is, well, let's game it out. When x is positive, this whole thing is going to be positive. And as x gets huge, this gets tiny. You're dividing 1 into more and more pieces to get smaller and smaller pieces, and so it's going to be getting smaller as we go out from the y-axis, and as we get closer to it, it's going to be enormous. So what we end up with is a shape that looks like this. Gets tiny, and it tries to get down to the x-axis. Never quite gets there, but it tries its best. And similarly, it goes almost vertically by the time we get to the y-axis. And then on the other side, it's the exact same thing, but in reverse. So it goes along the x-axis, then comes down for a vertical asymptote at x equals 0. And similarly on this side. This is what's called the reciprocal function. The name of this shape is a hyperbola, for those who want to know. It belongs to actually a similar family to the parabola from quadratic functions, but that's a matter for another day. And then we continue our gallery of horrors and get to the next one, the reciprocal squared function. And the formula here in question is f of x equals 1 over x squared. And again, the big difference between squares and non-squares is that when you square something, the result is never going to be negative. So unlike the hyperbola that we just drew, which had one side above and one side below, this one is going to have a similar shape, just both sides above. All right, now we're getting almost to the end here. The last two are the square root function which we write f of x just equals square root of x. And the way this looks is very similar to a quadratic function. It's just that because the squares are the undoings of square roots, what happens is basically what once was the x becomes the y, what once was the y becomes the x, and because square roots only ever give us a positive answer, we're going to have half of a parabola that goes up in that fashion. And then finally, the last item is the cube root function. And the way that looks is very similar to the square root, with the main difference, as usual, of when we are talking about cubes versus squares. Now negatives are on the table, which they weren't before. So it's a lot like this, except that there is a negative half to it as well. And so it looks like that. All right, well, there we have it. That is the material of section 3.1. Thank you, and I'll see you next time.